Which one is All right, good morning, everyone. So today what we'll do is finish up our discussion of just an overview techniques that are typically used to really explore metals and biological systems. And so in our previous lecture, we were focusing on the idea of, if you want to look at something in as accurate of an in vivo picture as possible, what are the considerations that we need to make at the level of extraction, at the level of purification, and then here we're talking about analysis. And so there are situations where extraction of, let's say, the tissue from a living system is needed in order to be able to gauge things. So what do we need to think about in order to try to preserve compounds, specifically those that involve metal binding? And there are those techniques that can help us to actually look at things when they are still alive, but they are quite limited still. So the technique that we ended up just introducing was mass spectrometry. And so this is quite a sensitive technique, but it often is a destructive technique. The requirement of a small amount of sample, it helps this to be a very useful approach to really gauging in the identification of different species, especially those that contain metals. And so one of the things that I had mentioned to you is that in order for you to look at things that contain metals, it's important to try to use a technique of mass spectrometry in which the ionization, that's the process in which the whatever species that you're looking at becomes into its ion form. This technique measures things that are in a charged state. So you want to use something that is soft. And what that means is that that conversion into the ion state should not break up or fragment the compound of interest or species of interest. And so one of the classical soft ionization, as I mentioned before, is electrospray ionization. And so it is a technique of ionization that has actually evolved quite a bit in terms of being accessible for many different types of samples, not just for small molecules. Thank you. Hi, I'm right here too. All right. We both in the opposite. Okay, so let's look at this a little bit more deeply then. So what I was mentioning to you last time is the importance of the homogeneous nature of your actual sample. And this comes really true when you're talking about proteins. And so I had mentioned to you that often when you're trying to recombinantly express protein, that's something that is pretty frequently used, especially in molecular biology, that you develop a system to be able to express protein, and whatever you use to be able to do so can lead to heterogeneous samples. So what do I mean by that? Well, a number of organisms, they produce glycosylation. Those are different sugars, and they do it non-selectively. So often you can have samples that have different glycosylation result in different masses. And that's why I'm emphasizing that, because this is a technique that depends on the measurement of mass. And so when you want to look at something that's of a protein nature, having a homogeneous sample is going to be very critical. And the way that typically is done is either you use a system like E. coli that doesn't result in glycosylation of proteins, or if you need to use some sort of, like, let's say, a mammalian system, well, then you need to use some sort of enzyme that's going to cleave this lack of homogenization of your actual sample. All right, so the use of mass spectrometry can give us quite a bit of insight in terms of trying to identify things, and in the context of metals, being able to detect the presence of metals. So we're going to look at here a few examples of how this technique is quite useful. So I'm going to start off with something that we're going to look at more closely in our next lecture, and that is a protein called transferrin. So there's a protein that is found in our blood and is actually the most important protein for the distribution or the biodistribution of iron throughout our whole body. So it is a protein that it's present in many different organisms. As its name implies, its function is as a transport of iron. So what we're looking at here are different electrospray ionization mass spectra of iron bound to the protein. And so this is a technique, as I mentioned before, that's mass by charge, right? So we're looking at things mass by charge. And so the protein itself when it's the intact form, and I'll mention this to you more closely next time, is 80 kilodalton. But in this particular experiment, so this comes from this paper here, 2001, they were working with a half version of the protein. So here we're looking at about 40,000. So that's a pretty big protein. But the way that you're looking at this is in terms of its charged states. So you can look at that the charged states that they're focusing on are the plus 12, the plus 13, the plus 14. So just imagine you take out your calculator, you plug in 40,000 and divide it by 12, divided by 13, by 14. Those are the actual species that are being detected. And that's important because these type of techniques have a limit of what masses they can detect. So you can see here in the x-axis, we're looking at something that's 4,000, but we're still able to see the actual protein because of a charge state that falls within the range. So typically, I think for electrospray, maybe up to 10,000 is what you can actually see. But the fact that we can exploit the higher charge states and be able to see that is why this technique has been quite useful. All right, so on the right is basically the charge states. But what you can do is zoom into a particular state. So let's imagine here, you zoom into one of these. So that is the plus 13, okay? So you zoom into there and what information can we get? So on the left side, you can't really see it that well on the screen here. But on the left side, what we're looking at are the different components of that protein that corresponds to just the protein by itself, okay? And then also there's indications of peaks that corresponds to the iron-bound form. And that's actually really important because with this technique, they can literally detect that there's a presence of iron there. So this was 2001. And so this was sort of the beginning attempt at using electrospray mass spectrometry for the purposes of identifying metals and proteins. A particular protein is a pretty big protein. But let's look at all the way to 2017. Now this has evolved quite a bit, and now the level of detail is even more precise. So here we're looking at the protein in its bilobal form. So that is the complete protein, which is 80,000. All right, so now we've doubled the mass. We're still able to see this protein, again, based on mass by charge, a particular charge state that we're focusing on here. And so what we're seeing here is the apoprotein, so the protein by itself. And then the panels B, C, and D, those correspond to the interactions of that protein with different metals. So we have indium here, we have chromium here, so you guys have been reading a little about chromium, and we have titanium here. So the use of this technique is quite valuable because it can tell you the presence of the metals and perhaps to some extent the amount of metallation of this particular protein. And it can also tell you to what extent is this protein metallated. So this particular protein can bind up to 2 equivalents of metal. So we can get an indication of, are there 1 equivalent bound or are there 2 equivalent bound? So it can be quite helpful in that sense. All right, and then here, same study, 2017, but this is even more powerful. What they were able to show is the interaction between the protein and its receptor. So now we're talking about this complex. And so the protein, again, 80,000. So let's keep track of that, 80,000. The protein's receptor is 160,000. In our next lecture, we'll talk more about this interaction and its significance, but I'm just calling attention to the masses. So the interaction between the protein and its receptor, well, it turns out that 2 equivalents of the protein, when it's metal bound, will interact with that receptor. And so we have this interaction here. So we have the summation of about 400 kilodalton that can be detected and the detail of a metal bound to the protein. So we have indium in this case that's bound, and we're looking at something in this charge state. So you see, you have to have a pretty high charge state to be able to see a complex that is huge, this 400,000 or 400 kD. All right, but mass spectrometry is also very helpful, especially at the level of small molecules. And so at the level of small molecules, especially with the type of instrument they use, you can benefit from having high resolution. So here's an example of the use of this particular technique, and I'm showing you titanium because one of those metals that actually has really nicely resolved isotopes. And so something that contains titanium, you would be able to determine based on the use of a mass spectrometer. So I'm just reminding you of the profile for titanium in terms of its isotopes. These are the common isotopes that you would find. So 46 through 50, those 5 are the most prevalent ones, of which, as you can see there, titanium-48 is the most abundant. That's why the mass of titanium is closer to 48, because that is the most abundant of the composition of all those isotopes. All right, So now, if a small molecule contains titanium, you should always see the presence of those 5 isotopes. And so on the left, we have an example of a titanium-containing small molecule that has the presence of at least 5 of those isotopes. You see there's a little bit more complex than that. And that's because you're also getting the isotopic distribution of the components of the actual molecule. So you're gonna have the contributions of carbon. We know carbon can have carbon-12, carbon-13, and so forth. So you have all that being compiled in there, but you should see a very distinctive, what's called isotopic distribution. So it's not just that mass spectrometry tells you the mass, but it also tells you the isotopic distribution. And if you don't get that match, then that tells you that you don't actually have the sample of interest, right? So you need to match the mass by charge, and you also need to match the isotopic distribution. And this is something that you can benefit from for small molecules. This is something that not necessarily you would see for bigger molecules because you lose out on resolution. All right, so continue on with this theme. Let me just clean this up. Actually, let me just go to the next slide. All right, so here's just another example of a titanium compound, and here to the right is just a visual of that compound. So titanium with 6 citrate bidentate ligands. So you have all 3 of them, 3 bidentate citrate ligands that are surrounding the metal center, giving you a coordination number of 6. So on the right, what you're seeing is something that if you do the math and try to determine the charge state, that's going to be a charge that's quite negative. I think it ends up being something that's anionic. But what I want to emphasize to you is that if you're seeing things mass by charge at the small molecule level and based on the technique, you will often see things that are of the charge of +1 if you're measuring them in the positive mode, or if you're measuring in the negative mode, it will be -1. And it is possible to see things that are +2, +3, but more common would be the +1. So the question is, using this type of technique, how can you determine the charge state? And there, the isotopic distribution is quite powerful because it can give you that information too. So here is a sort of a simplified representation of the data that you would obtain for that species on the right. And so again, you would typically see something that's +1. So the formulation, if you look up here, I'm showing you something up here to show you an adduct that forms of the compound in order for you to be able to see it. So we see that compound and it has proton adducts. Those proton adducts are important for you to get a charge that is +1. So what we have here in the picture below is the mass spectrum of the proton adduct with a +1 charge for that particular titanium compound. But how do we know from this data that it's +1? And the reason we know is because the distance in the isotopes, the mass distance has to be a mass difference of 1. So each of these isotope differences are a difference of 1. And that's a very powerful way of doing it. If you want to see something if you want to determine if it's +2 or 3, that difference, because it's mass by charge, would then be based on that. So if it's +2, then you would have a distance of 0.5. If it's +3, then you have a distance of 0.33. You can imagine if you try to go higher states, it becomes harder and harder. The resolution is just not going to be sufficient enough. So that's why this is more useful for these lower charge states. And then you can be able to be very convincing in terms of saying what type of species you have present. All right. So I mentioned to you last time this idea of using fragmentation as a way of trying to piece together the parts of a molecule to be able to identify it. So the technique of tandem mass spectrometry or fragmentation mass spectrometry is quite useful in that regard, and is normally referred to as MSMS. And so what we're looking at here is what information you get from tandem mass spectrometry. So the particular experiment, what it does, it measures the mass spectrum of the original compound, the parent ion. And then you apply a particular energy, or you can actually use the energy of gas to start fragmenting that molecule. So I'm just giving you this example on the right. Let's imagine that we're working with this particular selenium compound, the selenium sulfide bonded compound right there, where we're going to apply a fragmentation of it. So that's the whole compound. But then if we apply fragmentation, we're going to see the different pieces of that molecule. So we're going to have this piece here, and then we're going to have the other pieces that you can see of from the application of the fragmentation. So the MSMS, we're going to get the details of the parent, but also of the fragments, which also is referred to as the daughter ions. And so we're going to see the fragments that corresponds to 4, which ends up being the smallest fragment. And we're also going to see the fragments that corresponds to 2. So this one here is 2, as based on how it's cleaved. Okay, and then 3, based on how it's cleaved, this is the actual is the highest fragment. Okay, so using this information for an unknown can be quite helpful because you can piece together the daughter ions with the overall mass of the parent ions to try to figure out what you have there. You can take advantage, and people do take advantage of higher dimensions of fragmentation. So you can do MS3 to get then the granddaughter ions, MS4. Again, now more and more information can be a little bit overwhelming, but particularly in the field of protein proteomics, this is actually quite useful to get a lot of fragmentation in order to be able to identify a protein of interest. For small molecules, probably so much fragmentation may not be as helpful. Okay, but that's basically the information that you would get. All right, so what are the limitations of the use of mass spectrometry? Well, when you're doing tandem mass spec, the fragmentation process, a metal bound to that particular species may not remain intact. As you can imagine, you need that ligation system, and if you start breaking up the molecule, you may lose the contacts with the metal because of it. And then you often would need to couple in vivo experiments with the in vitro experiments. This is actually true of many techniques. It's not just mass spectrometry, that an isolated molecule actually does indeed bind a specific metal. So you need to have another technique that helps to confirm that that metal interaction is something that's actually real. So I mentioned this to you because I've also sent an email if anyone's interested. I know that you responded to me. I'm going to give a training on this particular MALDI that we have at the Molecular Science Building. There is another one that I'm not the one in charge of that one. This one is pretty really very easy to use, and you get a lot of output of data from the use of this. And it's helpful because you can do just a regular mass spec experiment, or you can actually do tandem MS experiments. All right, so let's look at another type of technique that's helpful. In a way, I'm going to do a little bit of refresher of the different types of energy-based techniques that have been useful in terms of characterization of different types of species. So spectroscopic approaches, this is the idea of absorption or emission of electromagnetic radiation. That's basically the premise of all these different techniques that we've been able to exploit in order to get insight into different compounds. So when you're looking at a system and its excitation, it's broken into all of these different components. The different motions that are related to translation, that's basically the movement of a particular species, the rotation, the vibrations within the bonds of the molecule. So you have all those details. So it depends on where in the electromagnetic radiation spectrum that you're looking at, which particular technique you're able to observe or you're able to take advantage of. And so here's just a representation of the different energies. So here we have it in terms of wavelengths and where we have the different types of energies that we take advantage of. So let's remind ourselves, radio, where do we take advantage of and what technique? You say Molotov, Carmen? Okay. Alex? All right, well, that's commonly used for NMR in that range. And then you have microwave, infrared, Carmen, you can answer that one. Exactly. Ultraviolet visible? Ultraviolet visible, UV vis. Okay, and so we're gonna focus on X-ray because X-ray actually is a type of electronic transition. So there's a few members of this course that are actually doing this type of experiments. They went away for a couple of weeks to do these experiments. All right, so X-ray absorption spectroscopy, or commonly referred to as XAS. A very useful technique, and we take advantage of X-ray because it can give us a lot of information at the atomic level. And so often people would use X-ray diffraction as a primary tool for characterization. Well, in the absence of, let's say, a crystalline material, and you want to get some insight into coordination, we're referring to metal compounds, you can still exploit X-ray technology for this purpose. So XAS is a technique that is specific to an atom. So what do I mean by that? Well, you need to apply a particular energy in order to look at an element of interest. So an X-ray photon energy range has to be used to look at these type of elements. And so what I'm going to show you here is the typical spectrum of an X-ray absorption. So here we have absorption versus energy. And what we're seeing are the different features. So we have this feature, and every feature is actually quite important. We have this feature here, the feature of which corresponds to Zanes. So you see there's a big spike in the absorption. And then you have a feature over here, which is the X-axis, which is this modulation. All right, so it's going to pick apart all these different features and what do they mean. All right, so in a typical X-ray absorption spectrum, you have the small rise in the absorption coefficient. So that's what I was mentioning to you over here. There's a small rise. And so what that small rise is due to is electronic transitions from the core level of the element. So these are the electrons within the core of that particular element getting excited to the valence levels, right? So from the inner orbitals to the outer orbitals. All right, so that's going to be just below the continuum. What I mean by just below the continuum? And what I mean is that still within the element without being ionized, without actually dissociating from the actual element. So this is referred to as the pre-edge. Then you have a really sharp rise. So that was what I showed you, that really big rise in absorption. So that sharp rise in absorption coefficient, well, that is a well-defined X-ray photon energy called the absorption edge. And so what this is due to is an excitation of those electrons that came from the core of the atom orbitals out of the atom. So they're actually getting lost from the atom itself. So you have the actual dissociation. And then finally, above the edge, there was that modulation section, the quasi-periodic modulation, which is referred to as X-axis. Okay, and that's actually a very important part, as we'll see in a moment. All right, so again, to remind ourselves, the different features here. We have the pre-edge, and we have the edge, which is a technique called Zanes that really explores the edge itself, and then you have X-axis, that's now what happens after the electrons are lost from the element of interest. All right, so let's explore that technique of Zanes. That is the X-ray absorption near edge structure. All right, so what we're looking at here are these different representations of core electrons from those orbitals getting excited all the way up to the valence orbitals. So we're looking at the different energies and the corresponding edge. So you have the K, when you read that, that's coming from the 1s orbital. You have the corresponding L ones that are going to be from higher energy, but still core orbital electrons. And these are what they're referred to. And so in order for you to be able to tap into those particular edges of a given element, you have to have a certain energy that matches that. So there's going to be a limitation of what energies are available, especially in the facilities where this technique can be done. There's going to be a limit of the energies that you can access. All right, so the accessible X-ray photon energy region, and I actually need to look this up to see if that's still correct. This is about 2 to 30 kilovoltage. And so in terms of the limitation of this technique, where you're going to have a limit is the actual sample holders, where you put your samples. And so that can give you, a little bit of a background. But as far as what is typically exploited are the K edges that are observable for those elements, and then the L edges that are observable for those up to this element right there. So going back, the K edge, those are the excitations from n equals to 1, the L edge n equals to 2, the M edge n equals to 3. So those are the core orbitals from which you are actually exciting from. All right, so why is this a valuable technique? What do we get from it? One of the most important things is the oxidation number. So then you can determine whatever species you're looking at, what is that charge? For metals, that's quite helpful. And it turns out that the higher the oxidation state of the absorbing atom, the higher the energy is going to be. So that makes sense because the higher the charge, those electrons that at the core are going to be more strongly held by the nucleus. So it's going to require more energy in order to be able to remove them from those core orbitals. Additional information that we get are the covalence, so the number of electron pairs, and the corresponding coordination number or molecular symmetry. So you get that information, coordination number and oxidation state. All right, so then the other part of this methodology, the extended X-ray absorption fine structure, or commonly known as X-axis. So what's going on there? So as I mentioned to you already, these are the electrons in the core of these elements. They're being dissociated. So as you know, these particular atoms, they're going to be surrounded by their neighboring atoms. So if you're looking at a metal, they're going to be surrounded by atoms that are coordinated to them. So what's going to happen is that those electrons are going to interact, they're going to hit the atoms that are neighboring, and there's going to cause this sort of wave length, this wave-like pattern that's causing for that quasi-periodic modulation. So it's simply that interaction between the electrons from the atom of interest interacting with its neighboring atoms. That's giving you this sort of pattern. So your absorber and your scatterers, and you can imagine that it gets quite complex there. But this is helpful because it can start to give you insight into the identity of the atoms that are surrounding your atom of interest. All right, so here I'm just showing you, and this is a very useful article. I haven't sent it to you, but basically it kind of guides you about all of the different data processing that you need to do. So you get the data, you do a background correction, just like you would do for many of the typical techniques in order to remove any noise. And then after that, you'll do apply a mathematical function to get the series of data that you have here. And that's the data that you start to actually fit in order to figure out what is interacting with the absorbing atom. All right, so what information do we get from this? All right, so XFs gives us the radial distance. So basically gives us information about bond lengths, depending on something's actually coordinated to the atom of interest. So it tells you how many of what type of atom are at what distance from the absorbing atom. And so here then you get identity of the ligand atoms, okay? But there is a limitation, and it actually can be quite a big one, especially if you're thinking about something that's biological, is that it's very hard to distinguish between oxygen and nitrogen. All right, so that is a big limitation. But oftentimes, the way you work around it is that you need to know your system, and you need to make educated guesses of what would reasonably be there based on what type of molecules are surrounding that metal, for it to be an oxygen or a nitrogen. So details like that can be quite important. You also get information about the bond lengths. Okay, so you get the structural information within 4 to 5 angstrom around the absorbing atom, and you also get the coordination number. Right, so here you start to then pick apart then the structural information of the coordination modality around that given element, or in this context, a metal of interest. Excuse me. So where can this type of experiment be done? So there are, I've seen, but I've never used tabletop instruments that supposedly offer the use of XAS, but you often have to go to an actual synchrotron light source to be able to exploit this type of technique. So that's where some of your classmates have gone, not to this one, they've gone to CHEST and Cornell to be able to take advantage of this type of technique. So getting access, that part is actually a rather simple process. So a lot of these synchrotron places, they ask you to write a proposal. So you have to write a short proposal of why you should get time to use the instrumentation. So you just have to justify the needs and how long. And so typically you put in, it's not something that you get necessarily charged for, but often they will identify what beam line, because not every beam line has the same accessibility of the energy, but who will be someone who can help you and what type of beam line you can use to do your experiment. All right, so what are the things that we need to take in consideration? So obviously for many of the techniques, it'd be useful if you can use pure samples, but the reality is if we're talking about things from an organism, that may not be so easy. So you can use in vivo samples, just keeping in mind that you're gonna have a mixture of things. So what's gonna be very important is to do what is called deconvolution. How do you deconvolute all this data to make sense of what you have in there? So helps to have the use of standards of expected species. So if you think that, let's say that you have a certain metal complex in this mixture, we'll actually take that metal complex with you, get its corresponding spectrum and compare, so you can be able to deconvolute your data. And so that's what people have done. So they don't necessarily take advantage of all the features. Some people can just rely on the Zanes part to make sense of what they have. So here's an example from the literature where they were looking at something that contained zinc. And so you can see the primary data was collected. That's the data up here. So they try to make sense of this data, excuse me.
Sorry to interrupt. Yeah. Before you keep going, can you go back to slide 54?
Damn it.
Yes.
Yeah.
So I have a question, right? Because from what you describe here, this is a similar technique to what we do in HNMR, right? Because we can see basically what's around the atom that we're studying, or the atoms
Right.
that are surrounding it, right? So, and you mentioned that we can identify the ligands, and like it can help to identify the ligands around the metal. So basically, we are able to exactly locate the the metal atom that we're interested in, and that way we can. So I'm quite confused on how can we
Right,
just
because remember, this technique is based on the energy. So if you
oh yeah.
apply the energy and you see nothing, then that thing is not there, unless for some reason you have a very, very low concentrated sample. But the fact that you see the spectrum means that you have your element of interest. Okay, so that just getting that data, that's the first good step. Like, I see my spectrum, therefore I definitely have my metal of interest. The next question becomes, well, what exactly is surrounding it? And that's where the use of XAFs can be quite quite powerful. I will say, so Javier, NMR has its limits. Whenever you're
Yeah,
working with magnetic metals, NMR becomes quite challenging because
exactly.
with the paramagnetic metals, you start to lose the resolution of things. You start to see chemical shifts being wildly distorted. And so is a lot more homework to do than if you have a diamagnetic system. Whereas here, you don't necessarily have that issue, right? You can just take advantage of the energy of the system to be able to see what metal you're looking at. But obviously, NMR is something that's more commonly accessible. This is something that you have to go physically to, or have a collaborator do it for you. I mean,
Yeah,
everything has its limitations, but yeah.
exactly.
Any other
Okay,
questions?
yeah.
Okay.
Thank you so much. Sorry to interrupt.
Oh, not a problem. All right, let's so we're looking at this example here. So they collected that data for the zinc containing sample, and then they ran standards. They ran a zinc phosphate, they ran a zinc cysteine, and they ran a zinc histidine because they expected that those type of things are going to be there. So as it turns out, by using this data, they were actually able to exactly fit their data by a composition of those three species. And so if you look at those numbers, there's a contribution of about 54% from the zinc phosphate, 25% of the zinc cysteine, and 21% of the histidine. Okay, so by that combination, they were able to fit this data. Does that exactly mean that all those three species are there? It means something like those species are there based on, remember, the coordination system of what's around it, because we don't see too far beyond, right? The sort of that primary shell of coordination. So similarly, you can do the same thing at the XAFS level. Again, XAFS is even more, there's more precision there. So here, an experiment was done to try to look at a nickel species in a plant. So they literally took I forget what part of the plant that we were actually looking at, whether it's a leaf or something like that. They apply it, and then they compared it to a nickel citrate standard, okay? And they basically get a pretty good match between the XAFS of the plant, that's the information in black, with the standard, the nickel citrate. So that implies that a dominance of a nickel citrate type species present in the actual sample that they were looking at.
Is there like a standard difference for the fit? So like if it is above this confidence in the fit, you can say that you have that.
Right. So there's going to be a confidence level that you have to meet. I don't know like a precise fit at this moment to tell you, but yeah, there has to be certain levels of like of a match for you to feel comfortable of what you're claiming. Yeah. Okay. And in this particular case, this was a pretty spot on because all of the actual peaks, and that has to do with the distance from the actual thing, you're hitting it on.
Itself.
The intensity is also important because there's a factor there, but you want to hit them both as best as possible. But here it's pretty good. I mean, you can see some issues at the end, but that's probably because of a distance issue more than anything. All right, so how to make XAS work for you. So for metal-bound proteins, you can also use small molecule standards, as we were just already mentioning, to predict the metal coordination in the metal binding side of what you're actually interested in. So if you have a pure sample, then by fitting the XAFS data, one can determine the primary coordination of the metals. But again, typical pure samples may be difficult unless you're working with something that's recombinant expression. And you can use educated guesses. So I've already mentioned to you that with XAFS, distinguishing between oxygen and nitrogen can be difficult, but you can figure out based on what you have in your system, if you know it fairly well, what is the most likely species. And especially if there's between nitrogen and oxygen, if you have like a double bond or a triple bond, then now there are going to be some differences that you're going to see there, right? With whatever's coordinated to the oxygen. All right, so here's just the profile of the electromagnetic radiation where we exploit NMR. EPR is electron paramagnetic resonance. That's like NMR, but for electrons. You have IR, UV-Vis that Oscar for some reason said that's MALDI, and XAS is right here. Okay. All right. Any questions before we move on? Yes, I just want to give you this insight because you're going to see a lot of this in the literature of techniques that have been used to try to characterize metal compounds. All right. So what we're going to do next, you have a question? All right, what we're going to do next, I'm upside down here. We're going to focus on a bit about transport because we're going to move into the direction of the transports of metal. So what I want to do is review things that you probably have seen previously. All right, so this is basically biochemistry 101, and then we're going to fine tune this so that we can focus on metal transport. So the idea of the requirements of moving things that are in solution through a membrane system. So I'm going to skip over this first slide. We already basically have been looking at that. So this idea of moving things, in your body as it goes into reaching the cellular environment. What are those factors that you have to keep in mind as it's undergoing transport into an actual cellular environment? This is a nice representation of the complexity of the cells and like the idea of membranes being surrounded by the actual cell itself, but also the organelles that are within cells. And this is a really standard picture that you see in a biochemistry textbook of an actual membrane and the composition of it, where you have this quite heterogeneous nature of the lipid bilayer, okay, and what's nestled in between there, where you have other lipids, you have transmembrane proteins here as an example, and then the composition of transmembrane proteins, where you have the components that are the exterior that tend to be hydrophilic, whereas the things that are in the interior can be hydrophobic in terms of it as the surrounding, but inside of it can enable things that are hydrophilic to move through. So just a reminder of how for us to think about the composition of biological membranes. All right, so let's look at it a little bit more with more specificity here. So when we're talking about membranes, these are lipid-based and they're pliable structures. So that means they can be quite mobile and they can be moved around. The thing that's important is this concept that their integrity has to be remain intact. Right, because as soon as you have a lysis event, it's hard for a cell to recover. You would just basically, a cell would undergo death at that point. So when you're thinking about the composition of the membrane, you have this mixture of lipids to proteins at a ratio of about 40:1. So some membrane lipids and proteins are glycosylated, and those glycosylation sites, those are the sugars or the carbohydrates that are on them, they're located on the exterior parts. Those are the ones that are coming into direct contact with the aqueous environment. So obviously all cells have membranes, and the purpose of the membrane really is to provide you sort of this internalized structure. It's to really importantly provide a compartmentalization of the different parts of your cellular environment to enable different types of processes to occur. So I want to draw your attention to this point that in red blood cells, these are the erythrocytes. Here, you don't actually have organelles. We have a large abundance of hemoglobin, right? So hemoglobin, that is a protein that we take advantage of in order for us to breathe. So our red blood cells are largely composed of that protein, hemoglobin. That's where the majority of our iron is located. All right, so what type of functions does the membrane play? So as I already alluded to, this idea of a compartmentalization. And in my previous lecture, I mentioned this point about how different interactions between molecules are actually affected by that compartmentalization, but also this idea of crowding. This effect that it can actually enable things that may not normally have an interaction, provides that reasonable affinity for a certain process to occur. So they define these external boundaries, but they also regulate the molecular trafficking or the trafficking of ions across them. They also serve for the function of cellular communication and also for signaling. And so we will talk about signaling later on as it pertains to events that are dependent on metals. They provide for this idea of discrete compartments to segregate different processes and components. And you'll often see this idea of complex reaction sequences that are involved with either energy transduction or molecular synthesis that are being done by particular organelles. All right, so let's look at this representation. This is what you would normally see in biochemistry of this this bilipid layer, where you have these leaflets, if you want to refer to them as that, where one of the leaflets will face the cytoplasm. So if you're looking at the cell membrane, or if you're looking at an actual organelle, you're focusing on the membrane itself. There's always one part of this that's actually facing the cytoplasm. But then you have the other component that's either, if it's a membrane, facing the extracellular space. And the extracellular space can be quite important, and it can be a little bit different from the blood environment or the inside of the actual membrane enclosed organelle. All right, so a few different features. So as I mentioned to you, pliable is a very flexible structure. We're talking about a thickness of 3 to 10 nanometers. So to an extent, they can also regulate what kind of things can actually enter. The structures of this bilayer are stabilized by non-covalent forces, particularly hydrophobic ones. And you have that the membrane bilayers largely composed of these phospholipids, where because of the nature of those phospholipids, you have a polar head that will be located on the exterior that forms that hydrophilic surface. And then you have the fatty acyl chains that are in the interior, and they provide this fluid environment. So when you think about the biological solvents, this is another component of the biological solvents, because now you have an environment that is not water-based, okay? And then you have quite a bit of lateral motion within the actual membrane itself. And you also have other lipids that are nestled in between the lipid bilayer, like you have cholesterol, things like that are really located there. All right, so now focusing on the protein component of the membrane. So there are two types of proteins, and this is super generalization. You have those that are the peripheral proteins. So those are loosely associated with the membrane of the membrane itself. And so there's something that with physical lysis, that these proteins can easily be isolated from the membrane. But then you have those things that are the integral proteins. Those are the things like, transmembrane protein that are really nestled in there. And so they are very difficult to extract, and their solubilization really depends on their presence within the membrane protein, which is the reason why a number of membrane proteins, when you try to separate them, their solubilization suffers because they're not quite soluble in aqueous conditions. All right, so these type of proteins, they span the lipid bilayer, and then when you look at the actual components of what they consist of, actually, I think I circled something that was not right here. The typical structure of the transmembrane part can be alpha helical or beta barrel. All right. Another really important part, and this is going to be the last thing that I want to emphasize, is the asymmetry of the actual membrane. So just as I already mentioned, the heterogeneous nature of the type of lipids or proteins that are located, some that are going to be preferably in the within the membrane, those that are going to be external. The carbohydrate moieties by glycosylation will be external. But another really important one is the idea that the membrane is electrically polarized. So going from the outside to the inside, you have this delta of negative 60 millivoltage. And that can be quite important in terms of this movement of different solutes through the membrane. And I already alluded to this idea of the integrity of the membrane. So important to maintain membrane continuity. So it's self-sealing, but it's very important that any process that's going to disrupt the membrane needs to be quite rapid so that it does not lead to natural lysis of the cells itself. So what we're going to focus on for the remainder of the lecture is this idea of the movement of different solutes. And so this idea of first defining the selective permeability of things that can cross through the membrane, and then explore transport that can be facilitated. All right, so this idea of a movement of our membrane transport. So here's a representation of different types of transport that can exist within cells. So the ones to the left, let's go through briefly. You have the type of movement that's called diffusion. So we commonly refer to this as passive diffusion, this idea of something just crossing right through the membrane itself. But there's also a type of diffusion that's called facilitated, and we're going to talk about that. What does that mean to be facilitated? Both of these fall under the category of diffusion. Then you have the type of movement that's called active transport, where you have the primary and then you have a secondary. We'll talk about that in a moment. And then you have the type of transporters that are referred to as channels. And so these are channels that regulate the movement of different types of species. And then finally, you have those types of molecules that are called ionophores. As the name implies, they are going to take an ion, they will bind that ion, and they'll move it through. And so in many contexts, ligands that form metal complexes, they actually play this role of an ionophore, meaning that their function is simply as a delivery. They bind the metal and they put it into the cells, and then that interaction probably breaks down within the cell environment, and the ligand doesn't really do much more than just the function of an ionophore. Right. Another type of transport is endocytosis. This is the idea of the membrane itself fully participating in the actual movement. So you're going to have an actual structural change of the membrane enabling this. So here we have this cartoon representation of the membrane forming into this type of organelle type structure that gets internalized and that gets endocytosed. And then you also have the corresponding process of exocytosis, which is the process of these type of organelle type species leaving the actual cellular environment. This representation is a simplification because oftentimes things that are endocytosed do not actually survive. So you don't actually get the exocytosis process. It gets broken down. But this is a representation of the two processes, being brought in and also leaving from the cell. All right, so this idea of selective permeability. What are those factors that are going to govern the movement of things through membranes? And so these are the four primary ones: the size, the hydrophobicity, the charge, and the concentration. So we're going to explore this in terms of these transport processes. All right, so here I provide you this table. It's a pretty simple table to kind of guide us through what we would expect to be permeable with for cells. And so the very top entry are for those non-polar molecules that, as an example, carbon dioxide, that are going to be permeable. But I put a little star here, and that star is actually supposed to be significant because it's true that non-polar things will be permeable, but there's going to be a size limit. We're going to return to that idea in a moment. Then you're going to have things that are actually small, uncharged polar molecules that are less than 100 grams per mole, and they actually are permeable. For instance, urea, water, ethanol, these things do actually cross the cell membrane. But then once you start getting higher in the mass, the molecular weight of the species, and then depending on the nature of their polarity or their charge, there are going to be limitations. So you're going to have things that are large, uncharged polar molecules like glucose that will not be permeable. So they're actually glucose transporters that are essential for the movement of glucose. You have things like ATP, which is a charged polar molecule that's also not permeable, even though that's a very important molecule. And you have ions, which can be as simple as just a potassium ion or something like bicarbonate that are also not permeable. So there's going to be something that's going to help facilitate their movement. All right, so going back to that star there, the nonpolar molecules and the restriction in terms of molecular weight. Well, it turns out that there's going to be a size limit. Actually, I should have looked this up. I don't know the exact cutoff of where you can expect things in terms of their size to be limited and permeability. But as you start to get things that are like pretty big, like proteins, you're going to have restriction of the ability of those proteins to get internalized. Often proteins, if they go inside, they're going to need some sort of transporter. But then I would say, as far as if you want to define some sort of cutoff, this is actually a useful one, and it's in the field of drug design. So this you get taught in medicinal chemistry, this idea of the Lipinski's rule of 5, and that governs this idea of what type of things people are looking to in terms of drug design in order for make something that might be orally bioavailable for the purpose of this, which is that you want to make something that is less than 500 grams per mole, because generally has been seen, but there are other details. That's why it's called Lipinski's rule of 5. I'm not going to get into it. This idea that you need a certain size limit in order for these drug-like things to be able to cross through the membrane. All right, so let's get into a little bit of the specifics about transport. And so here, let's focus a little bit about passive transport. So I already alluded to this idea of two types: the simple and then the assisted, the facilitated transport, diffusion. So when you're talking about the simple diffusion here, we're simply looking at
a diffusion that's occurring in the direction of the chemical gradient. So a gradient implies a concentration change. And so we're going to see this visually. What does that actually mean? And so this is what's applicable to, in that table that I already showed you, to non-polar molecules and also to small polar molecules. That, in contrast to then what is the diffusion in the direction of the electrochemical gradient. So here, that polarization of the actual membrane is going to be important. And it's applicable to polar molecules and ions, and it involves facilitation. So maybe there's some sort of membrane protein that's going to enable this process. Then you have what is known as the active transport. So here, you're going to have diffusion where you're moving against the electrochemical gradient. That is in contrast to what we're talking about when we're referring to diffusion, passive diffusion, where you're now moving against the electrochemical gradient and you have a facilitation by some sort of membrane protein. All right, so passive transport here is following the second law of thermodynamics, this idea that molecules are going to tend to spontaneously assume the distribution of the greatest randomness and lowest energy. So this idea of moving based on the concentration. So you have this really classical depiction of this movement where we're looking at simple diffusion, and the left is showing a system where you have a membrane that's separating the contents of the solution. And what we see is that there's a solute in the solution where you have C1, which is one concentration, C2 is the other concentration. We see that C1 is at a higher concentration than C2. But by this process of simple diffusion, and according to the movement with the chemical gradient, what's going to happen is that your system is going to undergo and reach this equilibrium where there's a movement of the solutes so that you essentially get the same concentration of that solute to be the same on both sides. Okay, so here at equilibrium, you're going to basically have no net flux. So basically, those concentrations will remain constant there. And now this is in contrast, well, not in contrast, but this is a little bit more complex version of that, where we're looking at movement, but based on the electrochemical gradient. So here, this will correspond to something that's charged. Over here, I didn't specify that, but this over here, what we were looking at, let's see. Here, I didn't specify charge, but basically this is more applicable to something that will be neutral. But over here, the charge is important. So what we're looking at is that before and after. Before, what we see are, in this solution, two different charge species, something that's positively charged and something that's negatively charged, and different amounts in both sides across the membrane itself. But then, as you reach equilibrium, what ends up happening? Well, you have now a flux of the anion and the cation through the membrane, such that at the end, you're going to reach charge neutrality. So now you don't have a difference of charge between both sides, and now you have satisfied this idea that you moved along the electrochemical gradient to try to balance out the concentration, but also the corresponding charge. Okay, so the electrochemical potential reaches 0 at equilibrium. All right, any questions about this? Yeah. All right, so in passive transport, yeah, go ahead.
Yes, so you mentioned about the threshold of 500 grams per mole, and that's for size. Yeah, but
that's for size.
Yeah, in terms of like very big molecules, now I'm not an expert by no means, but I know there's a lot of research undergoing into drug delivery systems. So these drug delivery systems take my guess is that they would take advantage of this method of transportation through membranes, right? So if you have a very big molecule, they will have the researchers would take advantage of this to try and deliver these type of drugs using any of these type of transportation methods to get the medicine.
Yeah, that's correct. Yeah, so often they're engineered to have something that may recognize a particular receptor or transporter, so that by the nature of that that interaction, it can get internalized. So yes, that's correct.
Okay, thank you.
So now when we're talking about the passive transport, again, we're moving along the chemical or the electrochemical gradient, And so at the end, you're going to have a system that's not accumulated above equilibrium concentration. So there's a process when you're looking at the Gibbs free energy, so delta G, that's going to be less than 0. Anything that's less than 0 is a process that's thermodynamically favorable, so exergonic. In contrast to something that's active transport. So here, you're going to be moving against the electrochemical gradient, right? And so you're going to end up accumulated above this equilibrium concentration. And what's facilitating that? So there could be a couple of things that's going to facilitate this process of active transport. So it's going to be something that's not thermodynamically favorable, right? So, but to make it favorable, you need to have something that provides that energy. And so you're going to couple this system either directly or indirectly, or it's not necessarily you couple it, but the system is coupled to something that's actually going to provide that energy. One of those things is going to be the breakdown of ATP. So we commonly refer to ATP as sort of that it houses energy. And that's in terms of its chemical bonds, the actual energy that's associated with that. But then you can also have the movement of another solute, that the energy of that movement is coupled with the energy of something that you're focusing on that can enable the movement. So that's another type of active transport. All right, so let's look at this representation of transport. And so here, and this cartoon on the right, we have this idea of something that is a charged species or polar. So I emphasize this for like metal compounds because they can often be charged in nature. So when something is polar charged, they tend to be, although it's not always the case, but they tend to be something that would be hydrophilic. But if you're going to think about this idea of crossing through, so meeting that sort of that 500 grams per mole threshold, you have to think about what's going to happen with that particular species for it to go through. Well, you have this layer of water surrounding it, right? But as I mentioned to you, the lipid bilayer is an entirely different solvent system. It's not something that's favorable for water. So in order for that thing to go through, there has to be this loss of water, this layer of water. And then for that to be stripped away, it goes through. And then at the other side, you'll have that species now coming again into an aqueous environment. It's going to get surrounded by that water layer. So what we see in terms of the energy profile for this transport process, if you want to think of this as a reaction, movement across, well, we have this profile here where we have this barrier, right? That barrier is the desolvation process. They're going through and then again, picking up the solvation process, and then you're back to where you were at the beginning. So this is something that in terms of the energy at the end, you regain the same system. So there's no difference in energy before and after. But then you have transporters that are going to accelerate this process. That's why they're called enzymes in the sense that they are speeding up the process, but they're not enzyme in the traditional sense of what we think about taking a substrate and converting it into a product, which that's going to lead to a difference in energy. Here, when you have a transporter, that's basically going to lower this activation barrier, because as we know, that activation barrier is what's defining the kinetics, how fast something's going to move. Something assisting this, you're going to lower that barrier and you're going to get something like this, which is the blue trace. I'm just tracing over dots. Well, now you've lowered that activation barrier and you facilitate movement. So as an example, we have this picture down here where you have that solvated system of whatever that solute is that is going to go from this sort of favorable environment into the inside of a transporter that's still giving an environment that's probably still favorable for it, more so than just going directly through the actual lipid bilayer. And so there's less of an energy penalty due to the desolvation process than the resolvation process. All right, so these are called permeases, again, enzymes that lead to the movement, but at the end of the day, you're not changing the nature of the species because you still have the same species at the end. So that's why there's no actual overall net change in energy. All right, so it ends up being that the delta G, in this case, double dagger corresponding to the transport is less than the delta G of the simple diffusion. All right, so representation of movement of solutes. You can have what is just a uniport through a transporter, that's just the solute itself going through, or you can have what is referred to as co-transport, where you have your solvent of, your solute of interest moving along with another solute, same direction, or the antiport against the direction. All right, so this directionality with or against the electrochemical gradient transporters can facilitate this by both passive and active transport. All right, so focusing on active transport, this idea of providing the energy so that something can move against its electrochemical gradient. So here we have this movement of S1 from outside of the cell into the inside, or into whatever this is an organelle. And so you're going from high concentration to low, you're going the opposite, the other way around. You're going from low concentration to high. So that's against the chemical gradient, but let's put this in the concept of electrochemical gradient. To be able to facilitate that, what's happening here is that ATP is going through a phosphate hydrolysis, so that now you're cleaving it so that you're forming ATP, an inorganic phosphate. And that's important because that gives you a significant amount of energy. This is a release of 30.5 kilojoules per mole. That energy is what's supplied into the movement of the solid one. Then you can have what is referred to as a secondary active transport. So here, you're coupling a couple of different things here. So let's look at this from the context of what we have going on here. So let's imagine that we have solid one, low concentration inside, high concentration outside. So for solid one to be moving in this direction, right, it's going to go against the electrochemical gradient. So that's being enabled by the hydrolysis of ATP. Right, that's what's facilitating that. But now solid one is actually going over here when it comes back, is moving along its electrochemical gradient, and it's supplying energy for a different solid 2, to be able to move in this direction. All right, so that's going to be an important part of this process here. All right, so this general classification of transporters, we can have them broken down into the channels and the carriers, and then within the carriers, some of the things that we already have mentioned, this idea of the active transporters or something that's a uniport. All right, so let's look at this from the perspective of the kinetics of transport. So here we have a profile of the transporter kinetics, and it's fit in a way like you would fit an enzyme kinetics. So this profile you would have seen in biochemistry, where you get an enzyme working on a substrate and converting into product. And so this idea of the enzyme, so the substrate interacting with the enzyme, and what we see is the corresponding velocity versus the concentration of the substrate. But here, in this context, we're looking at a metal, and a metal interacting with a transporter from this particular yeast. And so what we're focusing on is that zinc that's interacting with this particular transporter and at different concentrations. So we see something that's very similar to the Michaelis-Menten, where you have this increase in the velocity and you get this saturation profile. All right, so this increase, as you're increasing the amount of the zinc, because that zinc is interacting with this transporter, so more and more should be going through, but then you're going to reach a point where there's a saturation. And that saturation means that there's only so many different enzymes available or transporters available to move the zinc, so you're going to saturate it. So that's going to be your limit of how fast you can go. So this is very similar to what you see for enzyme kinetics. You get this very similar profile for the velocity, where this parameter here, KT, which is called the K transport, that is defined by the concentration of your, in this case, I say S, which would be your substrate, but it would be in this case zinc, or where you have the half of the actual maximum velocity. So let's clean that up just for us to look at. So focusing on this here, we're going to look at the maximum velocity, which is at about 16, right? For us to be at half, we need to be at around here, around there. So we can look at the halfway point. From here, we identify what would be the value of KT. And that's just a parameter that illustrates that particular enzyme. You see something down here as well. This down here is, this is an experiment where they use a vector to express their enzyme of interest. So the vector itself apparently has some amount of zinc transport, but you can see how the actual transporter is much more significant in terms of the movement of the actual zinc. And that's a control that's done just to know for sure. It's a type of activity assay to know for sure that the transporter is being effective. All right, so let's focus on channels, okay, as one of the types of transporters. So a channel is something that is a protein that forms pores in the membranes for diffusion. And so what we're looking at is these pores, and so here's the pores, these are closed, what happens is that they're going to open up when there is a signal. So it's a response to the opening up that there's a solid coming and you need to label that to come through. So this is the representation of that signal that's been reached. And so this signal can be in a few different ways. And so here, the depiction of some sort of charge signal, some sort of ligand that binds to the actual transporter, and that lets off the signal that you need to open up. Or maybe there's something that's going to cause a stress to cause that to open up, right? So these are the different ways that this message comes across, so the channel has to open up. All right, so there's a membrane electrical potential changes, or there's some sort of ligand binding that sets off that we need to open up this port. As a consequence of this mechanism, there's actually very low stereospecificity. And so this results in a movement, acceleration of the movement of the solute at several orders of magnitude greater than carriers. So channels facilitate movement much faster. And in fact, they approach the diffusion limit. You basically reach the maximum levels. But because you're not binding, there's no binding occurring between the channel and the solute, is not saturable, okay? So that's where this is different from what you would see from a normal enzyme. But let's see what happens, what distinguishes from a carrier. Now a carrier, there actually has to be a contact between the solute and the actual carrier. So what ends up happening is that there ends up being high substrate stereospecificity. So we have an example here of glucose, which we know that glucose is chiral. So here we have the representation of D-glucose being recognized by its transporter by its binding interaction that results in a signal to the protein that is coming to that contact. There's a conformational change. That conformational change is what basically now enables that molecule to come right through. But it is that direct contact. So that's why there is a stereospecificity, and it catalyzes transports at rates well below the free diffusion limit. So the big difference between channels, and they are saturable. Why they're saturable? Because they're points of contacts between the solute and the actual carrier, and there's only so many carriers available to facilitate this. All right, so that's in the category of transporters. But then I alluded to this idea of ionophores. So these are going to be molecules that participate in movement. And so in a sort of a classical representation, these are diverse class of organic molecules that increase the permeability of membranes to particular ions in terms of the living organisms. They can be peptide-based or non-peptide-based. And so an example of this is bacteria. They often produce peptidic antibiotics. And so the purpose of these antibiotics that's actually being created by the bacteria itself is because they use these molecules to inhibit the growth of other organisms. So it's a way of protecting themselves, because there's always a competition between bacteria. So they're trying to protect themselves by basically scavenging an ion that they're interested in. So a good example of this is this particular antibiotic is valinomycin, which is specific for binding potassium. And so you see this idea of the potassium, it interacts with this, this peptide, it binds and it gets brought in, and which facilitates the transporting. So something that's pretty commonly observed. You also have what is the receptor mediated endocytosis. And so this is the membrane itself part of it gets pinched off and actually gets internalized into the cellular environment. And so what we're looking at here is a sort of cartoon representation of different things that can be recognized by a receptor. But of those different things, you have this cartoon star, the protein, that is specific for a receptor. And that interaction sets up a signal to the membrane that it needs to internalize that protein ligand bond. And here, in this cartoon, I showed that there's something that's coding the actual membrane when that interaction occurs, because this process of endocytosis can be clathrin dependent. What do I mean by that? Well, clathrin is a protein that actually surrounds the outside of the membrane that's going to be internalized for this endosome. And so this clathrin is actually a signal. It's a signal for the endosome that forms, telling basically the inside of the cell, do not break up this endosome, because they want to actually recycle it so that it actually returns to the membrane. So that clathrin-dependent process is a significant one. You also have clathrin-independent processes, which is that there's no clathrin surrounding it. Basically, that endosome is being brought in to then be lysed so that they can take advantage of what's inside. Everything that's being brought in is going to be used. All right, so within this context, let's look at this idea of metal transport, but let's first look at it from the perspective of mobilization. So what do I mean by mobilization? Because mobilization sounds like transport, and it is, but oftentimes for different organisms to take advantage of metals, you have to be able to mobilize them. In other words, you have to be able to put them into a form that become accessible for transport. So let's think about how that's possible. So it's the idea of mobilizing metals so that they are bioavailable. And so there are some really principal ways that this can be done. And one of them is by chelation. So chelation, as the name implies, is that you use a ligand to coordinate onto the metal. And in that process of coordinating the metal, you make it solubilized. And this coordination interaction needs to be stable, but for bioavailability purposes, needs to be moderately labile. So what do I mean by moderately labile? Well, moderately labile refers to the reactivity of the metal. So you want to bind it strong enough that you can pull it out and make it soluble, but you don't want to be bound so tightly that that metal can no longer be used. So that's what labile means, that you have it coordinated, but you can release it so that it can be useful for whatever process. Another really important process is redox. That is the idea of changing the oxidation state of the metal. So often oxidation state, even a change of 1, is enough to make a metal quite soluble. Like I had mentioned to you about iron, iron is 2+ form is actually quite soluble. Iron is 3+ form is not. And then you have the act of acidification. And that is that the acidification process, and as you probably came across in your reading about chromium, can really affect the speciation of different metals and can enable their solubilization. One of the biggest things is that acidification can prevent metals from hydrolyzing, because sometimes hydrolyzing can cause metals to precipitate in a way that's basically irreversible. But oftentimes, the process of mobilization will consist of all three, or at least some 2 or all 3. It's not just one simple event that's going to be what's enabling mobilization. All right, so let's imagine that we are going to look at a mobilization in the form of chelation. That's the time I have here. I have a little time. All right, we're going to look at chelation. And so here we're looking at a system that exists within bacteria. These are called siderophores. So they're a family of molecules, and they're not very homogeneous. You see, they come in many different forms in terms of like how big they are. But one of their primary features, as their name implies, is that they have an attraction for iron. And so they have a coordination modality that is favorable for binding iron. So here what we're looking at is a siderophore that has the catechol moiety. So this is catechol that you were seeing here. And this is from a really well-known siderophore called Enterobacter. On the right, we have this ferroxamine B that has a different coordination modality. This coordination modality is the hydroxamic acid. So both of these are what type of chelators? Are they monodentate, bidentate, tridentate? What do you think? Carmen? Bidentate, that's correct. All right, so here we have the depiction of these compounds interacting with the iron. And so here we see the Enterobacter using all 3 of its catechols. So I only showed you one of them in the previous picture, but there are actually 3 of them. And what happens is that this molecule will wrap around the iron and it will form this 6-coordinated complex. And you basically now have all those catechols interacting. One thing that I want to emphasize to you is that in this ligation process, I'm going to just show this to you in this format here. You have the catechol. I'm just only focusing on the coordination modality. You have the metal. And when the metal interacts with that ligand, what's going to happen is that you're going to have deprotonation of the actual catechol. So that you have the 2 oxygens deprotonated like that, and then you're going to have the release of those 2 protons. Okay. I'm emphasizing that to you because there's a typical system that's used to represent metal ligand interactions referred to as the metal ligand hydrogen system. And so that defines the number of metal ligands and hydrogens that are in a given system. So often the way you represent this is that the ligand will be in its deprotonated form in this system. So that if we're looking at this enterobactin here, we're looking at a total of one metal. So let's look at one metal, ligand, and hydrogen. We have one metal and one ligand, right? So that's what we have here, because even though you have all three catechol, they're coming from the same molecule, and then the catechol has no protons, so then you have 0 protons there. So that'd be a representation there. On the right, we have the representation of the ferroxamine. So that's desferroxamine with the iron bound. And we have all three of the hydroxymic acid coordinated to the metal center, giving you a 6-coordinate species. And then you have something that's going to be very similar in terms of the metal ligand hydrogen representation as well. Okay. All right. So I'm going to see what we have. Let's look at this very last table. We'll end right here. This last table defines the different affinity constants, how strong those ligands bind. So these are enterobactin and a few different siderophores. And you can see that the enterobactin is quite high than some of these other ones, but they're all really high binding. You can see what coordination moieties they're using. But another really important parameter is the PM. PM is like pH, but it's a measure of the metals in solution. And so what that tells you is the following. The higher the PM value is, the lower the amount of iron in solution, because it's coordinated to that particular species, the lower free iron in solution. Okay. All right. So we're going to continue on from here in our next lecture. All right, everyone. Have a great weekend. He was not.